Enthalpy, entropy, and Gibbs energy are all state functions. Let's use this property and the definition of standard states and standard reactions to calculate delta H, delta S, and delta G for any reaction. Now, the standard Gibbs energy of reaction is related to the equilibrium constant through this equation here. Delta G naught is equal to minus RT ln K, the equilibrium constant. And we can also calculate the standard Gibbs energy of reaction from standard reaction enthalpy and entropy changes. Delta G equals delta H minus T delta S. These are two of the most important equations in all of physical chemistry. Now let's calculate delta G, delta H, and delta S of reaction. And we're going to do that from standard formation values. So the question is, what's a standard formation reaction? And the definition of a standard formation reaction is pretty straightforward. It creates 1 mole of product. There's only one product, and you create 1 mole of product in its standard state at a pressure of 1 bar, the standard pressure, and a specified temperature. And you do that from a stoichiometric mixture of reactants, and those reactants are elements in their standard state. So now the question is, what's the standard state? And of course, that depends on the element and the temperature. So let's consider standard ambient temperature of 298 Kelvin. Let's take a look at a specific example, the standard formation reaction of ethanol. A standard formation reaction creates 1 mole of product, only one product, and that product is in its standard state, which at 298 Kelvin for ethanol is a liquid. And the reactants are going to be elements in their standard state, that is carbon as graphite, H2, and O2 diatomic gases for hydrogen and oxygen, but each one with the appropriate stoichiometry to balance this reaction and form 1 mole of product. We have to set the 0 for the scales of delta G, delta H, and delta S, and that we do as the following. Delta G of formation and delta H of formation for all elements in their standard states at any temperature, we set those equal to 0. Whereas the third law of thermodynamics, that tells us that the absolute entropy of a perfect pure crystal is 0 when we go to a temperature of 0 Kelvin. Now, take a look at some arbitrary balanced chemical reaction. A plus 2B goes to 3Y plus 4Z in this example. And we can balance a reaction by using stoichiometric coefficients. Stoichiometric coefficients of 1, 2, 3, and 4 in this case. Now, how do we use a balanced chemical reaction to help us calculate delta G, delta H, and delta S for that reaction? We're going to do a sum that includes these delta G of formation values. And the way we do this is we're going to take a delta G of formation for each product. We're going to multiply each term by the stoichiometric coefficient of that product. We're going to sum up all the products, and then we're going to subtract off similar terms for each one of the reactants. Right? And again, we're going to take each delta G of formation of each reactant, and we're going to multiply by the stoichiometric coefficient, and we're going to do that for all the products and all the reactants. We're going to sum up the products, we're going to sum up the reactants, and we're going to subtract the reactants from the products. A similar scheme is used for delta H. Sum up all the products, multiplying each delta H of formation by the appropriate stoichiometric coefficient, sum up all the products, and subtract off all the reactants. For delta S, it looks a little bit different. Delta S for a reaction is calculated from absolute molar entropies. But again, we're going to take each product, we're going to take its absolute molar entropy, we're going to take its stoichiometric coefficient, we're going to multiply the absolute entropy by that stoichiometric coefficient, sum up all the products and subtract off all the reactants. Now the IUPAC defines not only stoichiometric coefficients, which were all positive numbers, but also stoichiometric numbers. And stoichiometric numbers allow us to write more compact and more mathematically appropriate way to do this summation. And what we've got here in stoichiometric numbers are they're signed quantities. The magnitude is the same. It balances the stoichiometry of the reaction, but stoichiometric numbers are negative for reactants and positive for products. Negative for reactants, positive for products. And what that allows us to do is to write these summations in a more compact and mathematically formally correct way. It does exactly the same thing as what we had before. We're still taking each delta G of formation for every product and reactant and just make sure that you're subtracting reactants and you're adding products. Each one, of course, each term multiplied by the appropriate stoichiometric number. So let's do a specific example, that of combustion of ethanol at 298 Kelvin. We're given all the appropriate delta G of formation values, and we're going to do a standard combustion reaction. So as always, you have to start with a balanced chemical reaction. In this case, it's going to be a standard combustion reaction. And a standard combustion reaction takes 1 mole of the organic molecule, in this case, that we're going to react, 1 mole of the molecule to be combusted, and you're going to react it with as much O2 as it takes to form CO2 and H2O. And if we're doing this at 298, then the O2 is going to be in the gas phase, CO2 is going to be in the gas phase, and H2O is going to be in the liquid phase. Our other reactant, ethanol in this case, will of course be in its standard state for that temperature. 1 mole of the species with enough oxygen to create a stoichiometrically balanced reaction that gives CO2 and H2O. That's a standard combustion reaction. To get delta G for this reaction, then, we need to take twice the delta G of formation of CO2 plus 3 times the delta G of formation of H2O, and we're going to subtract off all the reactants, that is delta G of formation for ethanol, and, oh yeah, oxygen is an element in its standard state, so delta G of formation is 0. We can forget that term here. And what we see as delta G for this reaction is highly exergonic, right? Oh, and this is a standard combustion reaction, so we also could label it as delta G of combustion with this C here. R is for general reaction, C is specifically for combustion. Now, oh, wait a minute. The next question is, what does this per mole refer to? And the answer is, you started with a balanced chemical reaction, and this per mole is per mole of the reaction as written. In this case, 1,324 kilojoules are evolved for every mole of ethanol that is reacted, whereas it's per 3 moles of O2 that's consumed, or per 2 moles of CO2 that is formed. So the Gibbs energy change calculated here refers to per mole of the reaction as written. Our first step is always start with a balanced chemical reaction. And then for whatever reaction you begin with, use the appropriate summation. Remember, it's always products minus reactants, but each term has to be multiplied by the correct magnitude of the stoichiometric coefficient. And just make sure then you do the full sum products minus reactants.